We're going to work through problem 4.7 of Taylor's Classical Mechanics, chapter 4. This problem involves work, potential energy, and the conservation of energy. So it says that we're on a planet X. The gravitational force on a mass m is vertically down. So we know that our force of gravity on this planet is a vector with 0I, and we're going vertically down, so it's negative m gamma y squared j. So that's our force of gravity, and gamma is not varying, it's a constant, and y is our height above the horizontal ground. So it says find the work done by gravity on a mass m moving from r1 to r2, and show that even though this is a different force of gravity than we're used to, it's still conservative. So let's find the work done moving from R1 to R2. That's going to be our force of gravity dot dr, which in this case is going to be just the y forces. It's negative m gamma y squared dy. And this will work out to be negative m gamma over 3 y cubed from y2 to y1. And we can see that our work done by gravity moving from R1 to R2 is negative m gamma over 3 y2 cubed minus y1 cubed. So this is only dependent on our final and initial positions. That's the key word. It's only dependent on position, which means that our force is conservative. So the force of gravity on this planet is still conservative, although it is different. Now we want to find the corresponding potential energy. We know that for a conservative force, our potential energy is going to depend on position. It's going to be the negative work done from moving to 0 to that position. And in our case, it's going to be the negative of negative m gamma over 3. If we go from 0 to a y value, we're going to have y cubed. And that's just going to be m gamma over 3 y cubed. That is our potential energy. So now we've found the work. We found the potential energy. That covers part A of this problem. Now for part B, we're going to thread a bead onto a curved, frictionless, rigid wire. It's going to extend from a ground level to a height h above the ground. And we want to show the forces on the bead when it is anywhere on this wire. So this is part B. You can imagine our wire looks something like this. And we'll start the bead up here, but this is when the bead is just anywhere on that wire. So the forces acting are going to be our force of gravity and our normal force. Normal force. This normal force can vary depending on speed, which means that it is not only dependent on position. So our normal force is non-conservative. Our force of gravity we just discovered up there is conservative. So we have a mixture here. And this will help us in part C. Part C, we want to say if we release the bead from rest at a height of h, how fast will it be going when it reaches the ground. Now, because we have conservative and non-conservative forces, we're going to have to use the concept that our kinetic energy plus our potential energy, the total of those two, will be a constant value. This is the conservation of energy. So our initial kinetic plus our initial potential will be the same as our final kinetic plus our final potential. Now, if our bead is traveling from a height h, we call this a height h, down to 0. That's where we're traveling along this path. Now, when it reaches the end, we're going to have a height of 0. So our gravitational potential energy is going to be 0 at the end. Now, we're starting from rest. No kinetic energy is there to start. So we know that makes our equation a lot simpler. It's just the initial potential energy is equal to the final kinetic energy. Our potential energy is m gamma h cubed over 3. That's going to equal our final kinetic energy. And we want to know what our final velocity is. So that's what we're solving for. Now we have 2/3. We can get rid of these masses from both sides by dividing those out. We have 2/3 gamma h cubed equals the final velocity squared. Take the square root of both sides. We're going to have our final velocity. We'll assume is equal to 2/3 gamma h cubed, the root of 2/3 gamma h cubed. So we found everything they're asking for. It's important to note that we had to use the conservation of energy here because we had conservative and non-conservative forces. It's also important to remember that the normal force is non-conservative, as it can vary with your speed, not only position.